Okay, let's talk about slope fields. First thing I want to do is I want to show you a couple of examples of what slope fields look like. And they're going to look kind of crazy, and then we're going to kind of work through why we do them and what they tell us. So here's an example of a slope field. So I kind of move that around so you can see it. That's kind of fun. Here's another example. Whoops. And here's one more. Okay, so all these little line thingies all over the place. It's like, what the heck is going on? Okay, so we're going to come back to seeing these in a second, but let's first find out where on earth, what's going on with these things. Okay, so let's imagine that I have a function. We'll call it function f. Okay, so I'm going to call it f of x. I don't know what f of x is, but I do know that its derivative is equal to, say, 2x plus 2. Okay, so I know that's the derivative. And let's say I wanted to graph the original function f. That's what I'm trying to do. I want to figure out what does f look like. Well, one way of doing this is you could try to figure out the antiderivative of f prime. That means like, hey, what did this original function have to be in order to get this as a derivative? And this one's not too bad to figure out. Let's see what happens. So we've got, so 2x. So to undo the derivative here, this would have had to have been what, an x squared term. And then let's see, the 2 would come, if I took the derivative of this, the 2 would come down out front, like I have right here, and this would turn into 1. So yeah, the antiderivative of 2x is x squared. Antiderivative of 2, let's see, is a constant right now, so before it needed to have an x on it. So maybe 2x, like so. So x squared plus 2x, that was my original function. If I take the derivative of this, this is what I get, right? Well, yes and no. This is one of the options, but what if it was, so I have x squared plus 2x, its derivative is 2x plus 2, but is there any other function that has the same derivative? And the answer is yes. There's an infinite number of functions that have this exact same derivative. For example, what if I had x squared plus 2x plus 7? Or that, because its derivative is 2x plus 2, because the derivative of 7 is just 0. Or what if instead of plus 7, it was plus 8? Or minus pi, right? Or plus 1,000, right? This constant value out here, it could be whatever the heck you want it to be, because the derivative of any constant is always going to be 0. So there's an infinite number of possibilities for this function f of x. So what we usually do when we're finding the antiderivatives is we don't know what that constant is or what it should be. So we usually just put a little plus, some sort of constant. So we put plus c to represent a constant. So this is the antiderivative of f prime of x. Now the problem with this, if I wanted to graph this, remember that's the original thing we're trying to do. If I want to graph this, that's graphing an infinite number of functions. It's like, what is that going to look like, right? In fact, I'm going to actually graph this with some different values of c. Let's take a look what it looks like. All right, so this is what this looks like. I've graphed like, I don't know, 30 or something of these iterations, and just at positive or integer values for c. So, here's x squared plus 2x plus 0, x squared plus 2x plus 1, x squared plus 2x plus 2. You see, it's a mess. And so you can imagine even if we graphed even more of these and did x squared plus 2x plus a half, or x squared plus 2x plus a fourth, and this is kind of a disaster looking type thing. So what a slope field's for is to help us visualize this without having to draw all these crazy lines. So let me show you what this looks like with the slope field superimposed over this graph. Remember, these are graphs of the possible graphs of f, right? The possible graphs of f based off of just the derivative. Okay, so here we go. We've got you see the little black lines on here? That's the slope field, and it's superimposed on top of this graph. And what's happening here is these little lines are, the way we find them is just the slope of the possible function at that specific point. And you see they actually line up nicely on this one just because it's a nice function and stuff like that. But it's like almost like grown up connect the dots. And you see as we follow this line down, we go this way, the slope gets a little bit more shallow, then 0, and it comes back up like this, right? So the slope fields help us visualize what the function might look like. Now let me show you the slope field now without the red lines on it. So here's the slope field without the functions drawn on top of it. I'm going to zoom out just a little bit. There we go. And you see, you can kind of see as if you're trying to play grown up connect the dots with these. I could come in through here and just make a nice little parabola right there. right? And so this shows, you know, the parabola could be up here, it could be down here, it could be way down here, right? This shows us all the possibilities of what this original function could look like without the mess of having to draw every single one. So here's another example, and so here's our slope field. And so this is helping us visualize the antiderivative of a specific derivative that we would know. And as if we played grown up connect the dots here, if I were to start down here, it looks like those slopes, and then we come up here and we have to kind of get a slope of 0 someplace in there, and we come back down and we go like this, and it looks like it's going to be some sort of cubic function. In fact, if I draw the antiderivative with a constant value of 0, let's see what that looks like. There we go, right there. I left this window over here because that way you can see as I move my C value up and down, right? You can see that graph right there, and this helps me visualize all these possibilities. By the way, this derivative of this one is, let's see, let's call this one G. Whoops, let's do black again. This is G prime of X. This is that second one I was just showing you. G prime of X is 3x squared minus 4. So that's the slope field I was generating. So the antiderivative of that, it's again not too bad of one. So see, the antiderivative of this would be x to the third power, right? I bring the 3 down. This would become a 2 as I took the derivative, and this would be minus 4x. And then plus our constant value. So this is the equation that we were just looking at with a C value that was changed. So here's x to the third minus 4x plus some sort of constant moving up and down. And you see the slope field helps us visualize what all those possibilities look like. Okay, so now that we've gone over what a slope field is, let's figure out how to actually figure, how to draw an actual slope field. So let's go back to this f prime of x1, and we'll figure out how to actually draw that one. Okay, so I've got the graph over here, and we're going to draw our slope field of 2x plus 2 onto this grid right here. And the way we're going to do it is we just go to, we're going to take any point we want. In fact, we're going to take a lot of points, and we're going to plug those points into our derivative and figure out the value. So for example, let's take a really simple one. I'm going to plug in 0, 0, right? That's the point 0, 0 into this equation right here. So my x value is 0, my y value is 0. Now this equation doesn't have it's not in terms of y. There are no y values, so I don't have to worry about that for this problem. But we will see problems with slope fields where there are x's and y's in this equation right here. They get really fun, crazy designs. So I'm going to plug 0 in for x. So f prime of 0 is 2 times 0 plus 2, which is 0 plus 2, so I get 2. Okay. What this means is my antiderivative, whatever equation it happens to be, at this point right here, it's got a slope of positive 2. So what I'm going to do is on this graph, I'm going to draw a little line segment that has a slope of positive 2. So here's 0. If I go up 1, 2, over 1, there's a slope of positive 2. We'll be connecting these 2 points right here. So I'm going to draw a little line, best I can, that connects those 2 points, just like that. Okay, and there's the beginnings of our slope field. And now I'm going to do that with a whole bunch of different points, right? Now, we can be smart about this. Like, for example, this point right here, this is 0, 1, right? Remember, our equation doesn't have anything to do with y. It just has to do with 0. So once again, for this point, I'm going to be plugging 0 in and getting the exact same answer out, which is a slope of 2. So up 2 over 1, so I need to pass through that point right there. So something like that, right? In fact, all of these points right here are going to have a slope of 2. Okay? Now let's try another one. So like this point right here, this is 1, 0. So I plug 1 into our equation, our derivative equation, and we get, whoops, plus 2. That's going to be what, total of 4, right? So over here I have a slope of 4, so up 4 over, like, very steep, right? Basically, yeah, very steep. It doesn't have to be perfect, just, very steep. Let's come back over here and do negative 1. If I plug in this point, negative 1, 0, plug in negative 1 into our derivative, and we get 2 times negative 1 is negative 2 plus 2 is 0, right? So at this point, my original function has, if it passes through this point right here, it's going to have a slope of 0. which is a horizontal line. Same thing with all these other points here because the y value doesn't matter. So at this point, if my function were to pass through that point, it would have a slope of 0. If my function were to pass through this point, it would have a slope of 0, and so on and so forth. And now you can start seeing this thing coming together. So if I were to plug in -2, so that's like this point right here is -2 comma 0. Remember, it doesn't matter what the y value is, so I'm plugging in -2 into my derivative equation. Equals what? -2 times 2 is -4 plus 2 is -2. So over here I've got a -2 slope. Something like that. And all of these are going to have -2 slopes. And guess what? All of these are going to have -4 slopes. And so on and so forth. And there we go. Now we have our slope. I mean, we could fill in these points over here too. I'm just too lazy to do it right now. But there's our slope field, the same thing that we had before. And if I play grown-up connect the dots, let's say that I know for a fact that my original function f, for whatever reason, I know it passes through this point right here, right? Well, then I could sketch a graph of it. I know it goes through here, so it's going to look something like this. Just play grown-up connect the dots like that. It's going to look a little bit like that. Just follow the slopes, right? And we have our parabola. Okay, that's what a slope field is. Let's try one, and let's try one more. This one, we'll try one a little bit more fancy schmancy. So let's clear all this off. Okay, here's a little bit more fun one. So let's say our derivative is x times y, all right? And we're not even going to worry about finding the antiderivative on this one. I'll show you what it is later, but it's a little bit beyond the scope of this problem. But let's say I want to know what the antiderivative of this thing looks like. You know, what are all the possibilities? So let's take a point. I like starting with 0, 0. So here is 0, 0 right here. So I'm going to plug the point 0, 0 in, 0 in for x, 0 in for y, and this one has both of them. So actually, I guess technically this should be f prime of x comma y, you know, like that. And those have two inputs, but that's okay. It's not, that's not important. 0 times 0 is 0, so I have a slope of 0 right there. Well, let's see, that's always going to happen. If we think about it, that's always going to happen anytime our x value is 0, which is all of these points right here. Doesn't matter what y is, I'm still going to, 0 times something is still going to be 0. So I'm going to have a slope of 0 all through these and down here. And also when y is 0, so all of these points along here, the slope is also going to be 0. So I'm going to put a 0 in on those too. Okay, so let's try another point. Let's do this one here, 1, 1. So I plug 1 in for x, 1 in for y. 1 times 1 is a positive 1. So I have a positive 1 slope. Looks something like that. That's going to happen, let's see, it's just that times, because if I plug in 2 times 2, that's a slope of 4, so that's really steep right there. Right, that's a slope of 4. Let's do this one, 2, an x value of 2, a y value of 1, so 2 times 1 is 2. All right, this is 3 times 1 is 3. 3 times 2 is 6, super steep. And 3 times 3 is 9. I don't even know how to draw a slope of 9, it's really steep. 2 times 3 is also 6. 1 times 2 is a slope of 2, right? 1 times 3 is a slope of 3. Let's go over here. -1 times 1, that's this point right here, right? X is -1 and y is +1. I multiply those together and I get -1. Here I get -2 times 1 is a -2, a -3. This one right here, -3 times 2 is a -6. Super steep. -2 times 2 is -4, and so on and so forth. Let me just finish filling this out. Okay, that finishes that quadrant. Now we come down here. -1 times -1. This one's going to be +1. This one's going to be, it's like, what does this thing look like? Right? +2, +3. And let's finish this filling this one out. All right, there we go. And we have our slope field for this function right here. And it's like, wow, what does this thing look like? And it'll probably be easier to show you on using Desmos, but that's what our slope field will look like for this. So on here, and this is the hard part, it's like, well, how do you know what it's going to look like? Let's say I know for a fact that my function passes through like this point right here. Well, in this case, what this one's going to end up looking like is like this. It's going to look like almost a parabola. It's more of a U or a fatter U shape than what I'm showing right here. But it could also, so I could do that, but if I come down here, let's say it passes through this point, let's do a different color. Let's say it passes through this point right here. well, then this one's going to look like this. It's upside down, right? You see that? Okay. So that's slope fields. Let me show you what really quick what this looks like on Desmos. All right, so here's my function right here. It's actually a exponential function with a quadratic in the exponent. It's e to the 1/2 x squared plus c. And so you can see what it looks like right there. And you notice, I mean, it looks like a parabola at times, but as I get, this is my h at 0, or my constant value at 0, excuse me. If my constant value goes negative, see how it's going to get rounder and rounder and rounder and rounder and rounder. Just how it happens that this function could also be negative. And so it could, appear down here as well. And you get the same kind of idea. So that's slope fields. You can find they're not terribly too bad, especially if you can find those patterns that help you fill out things like x is zeros, y is zeros, makes the whole thing go, things like that. So slope fields.